Welcome to the final part of this week's online lecture. In part 7, we will briefly discuss applications of infrared spectroscopy. Let's have a look then at some of the applications of infrared spectroscopy. Here we might have the infrared spectrum of a car exhaust. Why is this important? As you can see here, we've got water and carbon dioxide, as you would imagine. For when we oxidize a hydrocarbon, we would expect water and carbon dioxide as the products. And that is all we would expect to be coming out of the exhaust if the fuel was being burnt with 100% efficiency. There might be some nitrogen in there, so maybe nitrogen dioxide and nitrogen oxides would come out. But let's assume it was a pure hydrocarbon. However, what we see is incomplete combustion. We see some of the hydrocarbon coming out which is not being burnt. We also see carbon monoxide coming out because it's not being fully oxidized. This is a waste of energy, and some methane is also coming out of there as well. So this is a way we can analyze how well the engine is performing and perhaps whether it needs to be tuned. We also use infrared spectroscopy in order to identify functional groups in the molecule. It should be noted, however, that although it is a pretty good indicator of what functional groups are present in the molecule, you can't identify unambiguously what molecule it is. If you were given a choice, say, under exam conditions, is it this molecule or that molecule, then you can use the infrared spectrum to identify which molecule. But if you were just given the infrared spectrum and you were able to identify the functional groups, that wouldn't mean that you would be able to identify the molecule itself, not just from the functional group frequencies. So we can't identify positively a compound this way, although using the fingerprint region we can. Let's have a look at what I mean by that. Here we've got a couple of alkane isomers. We've got a CH stretch out here at some 2800 wave numbers or so. But we've also got CH bending modes, and these look pretty much identical. So in this group frequency region, beyond some 1400 wave numbers or so, we cannot identify the difference between the two molecules. But look at the fingerprint region. The fingerprint region is significantly different, and frequently this can be used to identify unambiguously what molecule it is. Here is an interesting molecule. This is a transition metal dimer with carbonyl ligands. We've got a couple of transition metals in the center, and we've got carbonyls either in terminal or bridge configuration. And we see carbonyl stretching bands at 2020 and 1830 wave numbers. I'm sure you're not surprised that the bands at 2020 wave numbers are associated with the terminal carbonyls. Notice that the 2020 is not too far away from the fundamental band of carbon monoxide itself, which occurs at 2146 wave numbers. But these bridging carbonyls, their frequency is around 1830 wave numbers, and that is not dissimilar to what you might find in a ketone that is around 1700 wave numbers. We spoke about intermolecular interactions. We can also do an analysis of hydrogen bonding using infrared spectroscopy. We might have an equilibrium set up like this, where my XH molecule can interact with my Y molecule through some kind of intermolecular interaction, perhaps hydrogen bonding. And we can monitor the intensity of XH and the XHY band as a function of concentration of Y. Notice that this is similar to what I was saying about the 1-butanol in carbon tetrachloride, where you can see a separation between the sharp and broad band, the broad band associated with the intermolecular interactions between butanol molecules. But there were some butanol molecules which were separate and showed us the sharp peak that it would have in the gas phase. A similar kind of thing is seen here. So we would be able to identify the equilibrium that is going on here because we can use the intensity of the XH and the XHY band as a function of Y to determine their concentrations, and so calculate the equilibrium constant. This is the end of my online lecture for week 8. Thanks for listening.